questions you have. It doesn't, because we'll work through it. You tell me one of the problems you're struggling with, we'll work through it and kind of get to the answer. If you have finished the assignment, you can hand it to me or you can turn it in on my desk. Just sit it on the keyboard. I will organize them into y'all's class at the end of the hour. What we're talking about today is transformations. Transformations are moving or changing a function to another. We're applying vertical. We're trying to apply transformations that change how the function looks. Now, there are very many parent functions. These are kind of the basic functions, and we apply transformations to them. All the parent functions that we have, the four that we're going to look at, are going to be these four here. There are others. There's lots of others. For every type of equation we have, there is a parent function for it. Cubics, x to the third has a parent function. X to the fourth, x to the fifth. Radicals, rationals, there are tons of them. We're going to have these four. Mainly, we're going to focus on linear, absolute value, and quadratic. The reason I say that is constant functions, in my opinion, aren't that interesting. It's just a flat line. Y equals 2. Y equals 1. We cannot apply a vertical stretch or shrink to it because it's a flat line. Really, the most we can do is move it up or down. So in the general form, 1 plus k, where k is the amount that we move it up or down. Literally, all we can do is we can move it up, we can move it down. That's it. So that's why I don't focus on it too much, because it's just up and down. That's about it. Linear, absolute value, and quadratic. Linear, line, equation of a line, y equals x is the parent function. And we call it the parent function because all other linear equations of a line are going to look similar to this here. Some of them might be steeper, some of them might be shallower. Some of them will move to the left, we'll move it to the right, we'll reflect it. We can have different properties, different transformations that can be applied to it. And the way we know it's linear is we have x to the first power, linear. The next one we have is quadratic, or sorry, absolute value. Can anybody figure out how we can distinguish absolute value from its equation? It has what? Absolute value bars. Absolute value bars tells us it's an absolute value function. And it has that V-shaped graph. So if we see a V-shaped graph, those absolute value bars, it's telling us it's an absolute value function. And again, we can move this, we can translate it, we can move it left, we can move it right, up, down, we can make it narrower, we can make it wider, we can flip it. And the last one's a quadratic. Quadratics have this U shape to them, this x squared, x to the power of 2. Now the domain and range, domain are the numbers we can plug in for x, and for all, well, 3 of these here specifically, linear, absolute value, and quadratic, we can plug any real number in for x. Because when we graph it, we're talking about the real number system, any of the real numbers. The range are the numbers that come out our y values. For a line, it's all real numbers. We can have any number. We can plug any number in, we get any number out. For our parent function for absolute value and quadratic, we will only have numbers greater than or equal to 0. Now that does change based off transformations, but we have these here. Types of transformation. Now for this here, we're going to write down the general forms. We have linear, absolute value, and quadratic. Now the general form for linear. Absolute value. And quadratic. These 3 here are the general forms. A, H, and K. There is one other letter we will put in there, especially when we start talking on 1.3 Wednesday, and that is a B. B is going to go in front of the X. Inside the parentheses are absolute values. Now, each of these here, A, H, and K, correspond to a type of transformation. A transformation we're going to apply to it, be it horizontal translation, vertical translation, horizontal stretch, horizontal shrink, vertical shrink, and reflection across the X and Y axis. And we use these here to signify what transformation is happening. When we look at the function, what is being applied to it. Okay? Now, we will keep coming back to this slide. I'm going to come back to it and fill in information as we go. I want to give you the whole equation at this point because I feel like it's better to have the whole equation than fill in the pieces of what is where, what is A, H, and K, what are they signifying, than trying to fill it back in as we go and add stuff as we go. Now, graphing, I'm not going to put a big emphasis on being able to graph everything 100%. Part of the reason, again, the reason I feel that way is there are graphing calculators, there are computers, there's stuff that will graph for us. As long as we understand how to read the graph, that's more important than being able to actually plot the points. I don't know how they do it in Germany, if they actually make you plot everything. Yeah, but understanding what you're seeing, I think, is more important, especially here where we can grab a calculator, it graphs it in 2 minutes, then you're just transferring over. Now, translations. Translation shifts a graph up, down, left, or right, but it does not change its size, shape, or orientation. All we're doing is moving it up, down, left, or right, or some combination of those. Two of the main ones, vertical translation. Vertical translation is going to be our K, and it's going to move it up or down. So depending on the value of K, what it is, it's going to move the function up or down. It's going to move the function up or down. And with this here, and with this value of K, it's going to be exactly what it looks like. And we're going to read it exactly as it looks. It's going to be easy for us to tell. Horizontal. Horizontal translation is going to be our H. It's going to move it to the left or to the right. H moves it left or right. And H is going to be, this value of H is going to be a little bit tricky because it's not what it appears. It's going to seem the opposite of what it appears. It's going to be a little flipped. So if we have a value for H, it's going to tell us that it's moving to the left or to the right, our horizontal translations. Vertical. Translation is our K, and it's up or down. So if we have a number in place of H, inside the parentheses, inside the absolute value bars, and it's being added or subtracted from X, it's going to either move left or right. H, outside those parentheses, outside those absolute value bars, being added or subtracted, is going to move it up or down. If there are no parentheses or are no absolute value bars, it's automatically outside. Questions on this so far? And again, we could just add those back to this here. I'm going to use the fact that I do have a computer. So if we look at this here, g of x equals x minus 4. So we need to determine which parent function this belongs to. It's not going to be constant, because constant is just a number. F of x equals 1 plus k. It just moves up or down. Because we do have an x, it's not constant. So it's going to be either linear, absolute value, or quadratic. Because x minus 4, is that going to be absolute value? Well, no, it doesn't have what? The absolute value bar. So it's not absolute value. How about quadratic? Well, quadratic has an exponent of 2 attached to that variable, yes? Either inside or outside parentheses. So it's not quadratic. This has to be what? Linear. Now, the parent function is y equals x. F of x equals x. You don't have to draw this, but since we know that it is a linear function, if we were to look at the graph, this would be the graph of the parent function. Y equals x, yes? And now we can see how the transformation is manipulating this or changing it. And in the general form, a times x minus h plus k. Do we have parentheses at all in this here for x minus 4? No, there's no parentheses specifically written, so we don't have an h. That means it's not moving left or right. But that 4 is taking the place of k, yes? What does k tell us? Where is it moving? K is up or down. How far is it moving up or down? 4. Which direction do we think it's going to go? So what's the sign with it? What's the sign in front of the 4? Because it's what? X minus 4, yes? So that is minus 4, negative 4. Negative is going to go down, yeah. So it would be down 4, which tells me that our new graph should be down here. We can just move everything down 4. And personally, I think having a picture or understanding of what happens is more important than just being able to graph it. And we will get these out and start using these some, but the graphing calculators, throw those out. F of x equals x. There's our parent function. And we said our new one was x minus 4. Did it indeed move everything down 4? Yeah. That's it. That's the whole answer. Let's look at g of x. G of x equals the absolute value of x plus 1. What would the parent function be? Absolute value, because it has the absolute value bars. Now the absolute value function is a v-shape, with the lowest part at the origin. That would be our parent function. F of x equals absolute value of x. Now, as we're looking at the transformations, a times the absolute value of x minus h plus k. Do we have a value for k? Do we have something being added to the end of it or subtracted from the end of it? Well, no. I mean, we do have 0, but that really doesn't matter, because I'm not going to talk about the fact that we moved it up 0, down 0. If we're not moving it, we're not going to mention it. But we do have a number inside the parentheses, yes? So h, our left and right, we're going to move it left or right how far? 1, yes? Because we're going to move it 1 unit to the left or to the right, because we have that 1 in place of h, yes? Now the question is, are we moving it to the right or to the left? The right. We all agree with right one? And luckily we do have the graphing calculator. We'll do this. It'll graph it for us, but we do have to go into menus to get absolute value of x. There's our absolute value, yes? So we are going to graph the absolute value of x plus 1, and it should move that blue graph 1 unit to the right for every point. Absolute value of x plus 1, graph, and we can see that the new red graph moved 1 unit to the right, yes? It actually moved 1 unit to the left, didn't it? That seems a little weird. Let's look back at the formula. Let's see what it is. Let me get a highlighter out. So our x's do line up, yes? In the general form we have, in the general form we have a minus. In the equation we have a plus, yes? Well, the only way I can change a negative, a minus to a plus, is with another negative, yes? Because a negative and negative make a positive. So really what this equation is saying and lining up with this h value is not so much that we have the absolute value of x plus 1, we do, but really what it's wanting us to see is that we have the absolute value of x minus negative 1. Because the only way we can change that or have it in that x minus h for here is that the h value is actually negative. Do y'all see that? Inside those parentheses are absolute values. It's going to be the opposite of what we think. Because again, it does look like it should be right. Plus is right. But inside these parentheses and absolute values, we're actually moving it to the left one. Because the value of h is not positive 1. The value of h in this case is actually negative 1. So we see how that's being affected. And the reason k up and down is not, because k, even in the general form, is what? Plus k. Because if that k value is positive, k value is positive 2, we just write plus 2. If it's down 2, it's minus 2. We don't write plus negative 2, we just say minus 2. It's exactly what we think it is. However, that left and right, because of that x minus h, that minus h, it's going to flip that direction. It's going to look the opposite of what we think. That's why this here is to the left and not to the right. Does that make sense? Yeah, it's a little funky. Questions on this up, down, left, right. We will do more of them. I think we feel pretty good with this so far, yes? Our next transformation is a reflection. A reflection flips the graph over a line of reflection. A reflected point is the same distance from the line of reflection as the original point, but is on the opposite side of the line, so we're flipping it across. Now, the main reflection that we'll look at here, or the main reflections that we have, is a reflection across the x-axis. And if we have a reflection across the x-axis, the a value, a is negative. The number in a spot, wherever a is, that number outside the parentheses, outside the absolute values, if that number is negative, it's a reflection across the x-axis. Now note that I'm not talking about the value of A. I'm talking about a sign. Because a specific number, the number for A, is connected with vertical stretch or shrink. Its sign is connected to reflection. So if A, the number in a spot is negative, it's telling us the reflection across the x-axis. If the sign inside the parentheses is connected to x, so such as this here or this here, if that negative is inside the parentheses in front of x, or inside the absolute values in front of x, this is not a reflection across the x-axis. This is a reflection across the y-axis. Normally we would connect this with b. B is going to be the number in front of that x in there. I just did not write it up there at this point because I think a, h, and k is enough to focus on today, let alone throwing in this fourth variable. Now for us here, reflection across the y-axis just straight to the parent function doesn't do a whole lot because it's going to reflect the function onto itself. It's going to give us the exact same function back. So if we look at this one here, the graph p of x equals negative x squared. So we want to determine or say what the parent function is. Well, its parent function would be the what? Absolute value? Linear? Constant? Quartic? When you talk about quartic, it has to be what? Quadratic. It's a quadratic function, and we know it's quadratic because of the x squared. Quadratic is this U-shaped graph. This is our f of x equals x squared. This is the parent function. Now we can see here, as we just talked about, our general form, a times x minus h squared plus k. That negative is in the a spot, yes? Now the value of a is 1. We're not so much focused on the value, the negative. Because it is negative, it's telling us it's a reflection across the x-axis. Not because the number is 1, but because it is negative. Since that number is negative, it tells us that we have a reflection across the x-axis. It means every point on the parent function, that U-shaped graph that's above it, is going to now be below it, yes. So that means it's now going to be going this way here. Can we kind of see how that works? And this, again, this is why I say having an understanding of being able to picture what the graph is doing is going to be bigger and be more helpful for us when solving than just being able to graph it. There's also y equals x squared, negative x squared graph. It'll do it for us. But if I can interpret and know what it's doing, it's going to be a lot better. And this especially comes when solving. If I know if it's going to cross the x-axis, because it crossing the x-axis is the solution for a lot of equations. If I know in my head I can see the picture of it and see, okay, that's not going to cross the x-axis or shouldn't, it makes things a lot easier. What parent does this belong to? Linear, constant, absolute value, quadratic? It is. So constant, we have no variable. We do have a variable here, yes. Quadratic would need a square. Absolute value would need the absolute value. So this is indeed linear. I'll go on, since I've been giving rough graphs of these all day, might as well go on and give it another one. There is no h, there's no number added or subtracted x inside the parentheses. There are no parentheses. There's no number added or subtracted to it, so that's telling us it's not moving up, down, it's not moving left, right. The a value is indeed what? Negative. Since it's negative, it is a reflection across the x. Reflection across the x-axis. Which means all these points here are going to be reflected in equal distance below it. However far above the x-axis it is now going to be that distance below it. All of these points over here that were below it are now going to be above it that same amount. Questions on this here? Funny enough, with lines, especially the parent function, reflection across the x and y axis does the exact same thing. Because by definition, it would be moving all the points from here to here, and all these points from here to there. Let's look at these last three. G of x equals x plus 3. What parent function would it be a part of? Linear. You don't have to write the general form above it each time. I'm writing it just so we can visually see how does this connect, what goes where. Because especially with these transformations, it's more important, especially when we're starting working this and seeing it, what does each value connect with? A, H, K, eventually B, which one is they going with? That plus 3, that positive 3, is it going to go with the A, H, or K? K. So since it's a part of K, that tells us that it's going to be moving up or down. How far? 3. Now the question is it up or down? Up. Up and down is exactly what we see. Plus 3, positive 3, up 3. Yep. Up 3. That's it. The quantity x minus 2 squared. What parent function would it go with? Quadratic. There is no k. There's nothing being added outside the parentheses, but we do have that x minus 2. That minus 2 is connected to our x minus 2 that is going along with our h, which means we're moving to the left or to the right. How far are we moving left or right? 2. Now the question is, are we moving to the left or to the right? Almost to the right. Because again, left and right, inside those parentheses is the opposite of what we think. Because is the main way I think of it. Because if we look at this here, x and x do line up. X in our function, x in the general form line up, yes? Well, hey, here, the minus and minus do line up to the general form, which means our value of h in this case is positive 2. H is positive 2. Positive is to the right, so it would move right 2. It looks negative, but the value of h is positive. That's why we have that opposite motion. Does that make sense? I think the easiest way is just to remember left and right, opposite of what we think. If negative is going to move x minus 2, moves it 2 to the right. If it was x plus 2, be 2 to the left. Last one, negative absolute value of x. Well, this is absolute value. Because, I mean, we just said it. Negative absolute value of x, absolute value. The negative is taking the place of a. Yes? So this has to be a what? Reflection across the x-axis. Because absolute value of the parent function would be a v-shape going up. Negative absolute value of x is now v-shape going down, opening down. Questions on number 4. So I won't do any other problems, but the last thing I want to talk about, vertical stretch, vertical shrink. What this is doing is making the y values, as we're going up or down, faster or slower. When we stretch it vertically, it's going to get narrower. When we shrink it, when it's a vertical shrink, it's going to open up faster. And we will talk about this, especially tomorrow. Vertical stretch. We know it's a vertical stretch if a is greater than 1. I'm not talking about the sign. I'm talking about the number itself. Because if in the a spot we had, say, negative 2, 2 would talk about the vertical stretch or shrink. 2 is greater than 1, so it would indeed be a vertical stretch. But the negative 2, our negative, again, is talking about the reflection. The negative with a is our reflection. The 2 is talking about the stretch or shrink. We look at the number specifically to determine if it's stretch or shrink. We look at its sign to determine if there's a reflection. Now it's a vertical shrink if 0 is less than a is less than 1. If a is between 0 and 1, it's a shrink. If a is greater than 1, it's a stretch. Now the technical definition for this here, for stretch and shrink, is we'd say the absolute value of a. If the absolute value of a is greater than 1, it's a stretch. If the absolute value of a is between 0 and 1, it's a shrink. They're doing that to get rid of the negative, to not talk about the negative. But I think we have the wherewithal to say the negative, if there's a negative with a, that's reflection. The number itself is telling us stretch or shrink. If the value of a is 1, there is no stretch or shrink. Questions on this here? Okay, we'll stop here.